Welcome, everyone, to today's Passive House Alberta Building Better in Alberta webinar series, sponsored by the Alberta Eco Trust. My name is Frank Crawford, and I am the Education Committee Lead for Passive House Alberta. Today's presentation is about mastering control systems for optimum heat pump performance, and our presenter is John Kokko, who is a licensed professional engineer and certified commissioning professional with over 30 years of experience in the building and controls industry. But before we hear from John, Joe from our sponsor, the Alberta Eco Trust, would like to say a few words. Joe?
Thanks, Frank. Appreciate that. I won't take long. I just wanted to make sure I introduced everybody to Alberta Eco Trust as well as our two buildings initiatives. So Alberta Eco Trust, we're a charitable foundation in Alberta. We've been in operation for over 30 years, and we support environmental action through various grants and programs. More recently, we have started into more direct initiatives, including our two buildings initiatives. So the first one is our it's our NMIX. The NMIX is the Emissions Neutral Building Information Exchange. So we work to bring all aspects of the building industry together in order to share knowledge and build capacity when it comes to producing an emissions neutral built environment. We do this across all types and scope of building. We work with every aspect of it, and meaning that we're not just focused on strictly emissions neutral. Anybody who's on that path to higher efficiency is, I kind of consider them to be on that journey towards emissions neutral. Our other buildings initiative is our Retrofit Accelerator. Our Retrofit Accelerator offers free coaching services for building owners and managers. This works on a system where we're trying to explain how a deep energy retrofit works and how an owner, or manager, and operator of a building can access those services. And then in addition to that, we are working with our community of renovators and contractors and engineers and designers in order to make sure that the skill set exists to support deep energy retrofits in Alberta. So yeah, that's a little bit about our buildings initiative. So Frank, I'll hand it back to you.
Perfect. Thank you, Joe, and thank you to the Alberta Eco Trust for their ongoing support. It is very helpful in allowing Passive House Alberta to continue our work. So as always, if you have any questions, please put them in the chat box and I will ask them at the end, or you can always unmute at the end if you prefer to ask them yourself. So with that, John, why don't you share your screen and take it away.
Okay, thank you very much. I guess I'm unmuted. I am unmuted, so thanks for the opportunity to bring this presentation. It is one that was developed by Natural Resources Canada on control systems for heat pumps. And we're looking at how can a heat pump performance be optimized by using different control strategies. So we will be talking a little bit about current controls that are out in the marketplace. We'll look at 4 different control approaches that can be used. And then we'll look at a detailed review of those approaches, followed by a case study on what it looks like from an energy, a cost, and a greenhouse gas emissions standpoint to use each of those. And then we'll wrap it up with what was presented. But I've also got some additional information on heat pumps and some design considerations, that sort of thing. So we are talking about heat pumps with backup. Now, backup can be electric or gas. And with an electric backup, the heat pump will run continuously over its full range of operation. So if it can go down to -30, then the heat pump will run down to -30, and the supplemental heat will come on with our electric supplemental will come on when it's needed to maintain the load in the house. But the heat pump does continue to operate, and so the two are running simultaneously. With a natural gas backup, generally it's one or the other runs. So the heat pump will run down to whatever control set point is set up, and then the heat pump will come on to replace the electric heat pump heating when it's needed, but only one of the two runs at a time. So what we're going to talk about are four different heat pump control options. They're known as outside temperature balance point cutoff, single temperature economic cutoff, a two-stage temperature-driven cutoff, and a two-stage time-based cutoff. And we'll explain each one of those as we go. And like I say, this is for gas backup heat. The examples are for gas backup heat, but it can be used in either for either the electric or the gas. So why would we want to look at different control options? Well, obviously costs are a big issue. Comfort is an issue. For contractors, you want to be looking at competitive pricing as well as customer satisfaction. And from a societal perspective, we want to look at our energy management. We all know that the energy is a big issue these days, both from a use point of view, but also from a supply point of view. And as our little friend in the corner here says, let's not forget about carbon emissions. So we are going to be discussing a hybrid air source system with gas backup, as I said. And when we get to the case study, it's looking at a house with a 14 kilowatt load, but the heat pump nominally has a 10.5 kilowatt output. And so we can almost immediately see that we're not going to meet the whole load of the house. So what happens with heat pumps? Well, a house heating load starts from pretty much zero at some higher outdoor temperature, but as it gets colder, the heating load goes up and goes up. And in like this is a Calgary situation or a Calgary case study, so we're looking at about a minus 31 design temperature, and that at that point we're about 14 kilowatts of heat load on the house. The I guess one unfortunate or different issue with heat pumps is the capacity does drop as the outdoor temperature drops. So while our heating load is increasing, the output from a heat pump is decreasing, which doesn't sound like a very good match. But at some point, there's what's called the thermal balance point or outdoor temperature balance point. In our example here, it's minus 6.8 or almost minus 7 degrees C. So below about minus 7, the heat output of the heat pump won't keep up with the load of the house, meaning the house is probably going to start cooling off a little more than we would like. The next part of the equation is that the coefficient of performance or the efficiency of the heat pump also drops as the outdoor air temperature gets colder. So while the manufacturer may say we've got a COP of 3.5 or something, that's usually at a very high temperature. So if we're looking at what heat pump we're going to put in, we got to be careful to recognize that not only does the capacity go down, but also the energy efficiency of the heat pump goes down. I am assuming here that everybody is familiar with the COP on a heat pump, and that means that it is the output of the heat pump in units of heat versus divided by the input. So a COP of 3 means we get a heat output from the heat pump of 3 units of energy for every 1 unit we put in. And that's because we pick up 2 units of energy from the outdoor air, add 1 unit of electrical energy from the compressor, and that gives us 3 to put into the house for 1 we put into the house for 1 of electricity that we put in. So our first approach, the outdoor air balance point temperature cutoff. Slide says -6. I said -7. So we're in that range. What the graph shows us is the typical meteorological year. This is how simulations are generally done for what is the outdoor air temperature every hour of the year, 8,760 hours. And if we look at this top orangey bar, then that shows us from the outdoor temperature at which we need to start heating to this balance point of, actually in this graph it's -7. We are going to be using the heat pump only. And then once we get below -7, the heat pump turns off, and the pink area shows us that we're now in gas backup only. The interesting thing here is if we ignore the summertime when we're not going to turn heating on most of the time anyway, we do get about over 50%, about 54% of the hours are covered by the heat pump we're using in this example. And only 46% or so comes from gas heating. The other nice side of heat pumps is because they do reverse, we do get heat pump cooling, so we can get air conditioning in the summertime for the with the same use. So what this says is heat pump starts to heat when the house needs heating. It will heat until the outdoor air temperature gets to about -7, and then it'll flip over when the temperature is below -7 and run the gas. And when the outdoor temperature rises above -7, the heat pump comes back on again. Control approach number 2, single point temperature economic cutoff. This is a little bit more complicated because we're looking at what is the COP at which the price of electricity is such that it's going to cost us more to run the heat pump than using gas. So in this case, we were talking about this a little before the seminar started, but Alberta has got very complicated energy pricing, and it changes continuously. So I've tried to use sort of an average over the year and said the price of electricity is about 2.5 or a little bit more, 2.8 times more than gas on average over the year. So that means once my COP drops below let's call it 2.5, my electric use with a heat pump and a COP of 2.5 is going to be more expensive than using gas. And for this particular example, that turns out to be about 3.3 degrees C, plus 3.3. So if we're going to use that economic cutoff point, it says we're going to bring the heat pump on when our heating season starts, and we're going to let the heat pump run down to about plus 3.3 degrees C outdoors. Below that, we're going to run gas heating, and again, when the temperature rises to about 3.3, then we turn on the heat pump to run above that temperature. There is a sizing tool that I'll talk about a little later that Enercan has that can help determine this economic balance point if that's the strategy you're interested in using. And in this example, we get about 35% of our heating hours are met by the heat pump using a economic cutoff temperature. Control approach number 3, two-stage temperature driven. So what this does is when in let's call it warmer temperatures, the house is at a set point of 22. It starts to cool off. We've got a offset of about half a degree, so at 21.5, we say, okay, let's bring the heat pump on, bring the house back up to temperature. As long as the heat pump is able to bring it up to temperature, we're all good. We use heat pump only, and it turns off. Then we start that cycle all over again. However, at some point, it's going to get to the point where the heat pump, instead of being able to keep up, the temperature in the house is going to continue to drop. So we are running along nicely. The house cools off, hit that first stage of, the first temperature point. It turns the heat pump on. Heat pump continues to run, but it can't keep up with the load, and the house temperature drops to stage 2. At that point, we say, okay, the heat pump is not going to be able to heat us back up. So let's turn the heat pump off, turn the gas heating on, bring us back up to the set point and carry on. And that will then carry on again, start all over again. And if the next time it can't keep up again, it'll do the same thing. If the next time it comes on, oh, look, the things have warmed up a little bit and we can keep up, it will do what I showed in the previous graph here. It'll turn on and come back up. So it makes a decision based on whether it hits this second point or not as to whether to bring on the gas heating. Then approach number 4 is that control approach, the two-stage time-based. And what that says is, let's, the house is coming along. It drops down to the heating turn on point for heating. The heat pump comes on, and it's given a certain time to see if it can hit the set point again. So in this example, it's 15 minutes. It could be 10 minutes. It could be half an hour. It's up to whoever is setting it up to decide what that time frame is. And then if the heat pump in that time frame can't hit set point, so it can either come up a little bit, it can go down a little bit, it doesn't matter. It says, okay, 15 minutes later, have we hit the set point in the house? If yes, then turn the heat pump off. If no, then turn on the gas backup heating. So that's our 4 different strategies that we're looking at. There's all kinds of thermostats out there that either third-party thermostats or dedicated thermostats that come with the heat pump that may or may not have all or some of those different strategies. So case study, let's see how these things actually work. So we've got a house that's got a heating load of about 14 kilowatts. And there's different units, but they're all 14 kilowatts. Cooling load is about 5.6 kilowatts. It's got a 65,000 BTU an hour furnace, 96% efficient. It's an older house, built in 1980, almost 2,300 square feet. Important things are what's the CFM that the actual ductwork in the house can carry at what static, and we'll get into that, as well as what is the panel size? 100 amp panel. And just to take a little diversion here for a second, one of the reasons for possibly keeping gas, other than it's, it may be economic, is if we've got just a 100 amp panel in the house, um, and we don't want to have to upgrade that because it can cost a few $1,000s. The gas backup may allow us to use a heat pump with gas backup without those extra costs. So the homeowner wanted to see if they could find some resilience to changing energy costs, which in Alberta might be a little bit of a tricky situation. They want to reduce their reliance on fossil fuels, and they want to manage their costs and minimize disruption and renovation. So this is why, with the 100 amp panel, they decided to use gas backup. So if we look at strategy one, our outdoor temperature uh, thermal cutoff. So then, let me sort of note here. The gas price we're using is an annual average of about $11.40 a gigajoule, and an average electricity cost of about 15 cents a kilowatt hour. These are the variable costs only, the ones that changing from a heat pump to a gas furnace, or from a gas furnace to a heat pump will impact. The fixed costs have been left out because they're going to be there regardless, and GST has been left out because it's going to be applied to everything as well. So on the economic cutoff point, no great surprise. Gas right now is a little cheaper in Alberta than is electricity. And so that the operating heat pump at the thermal balance point can be a couple of $100 more, 13%. So that's if economics is the only consideration, that is what people would be looking at. But we know that the costs of electricity and gas do change pretty dramatically, even from month to month. So it's going to be something that needs to be looked at pretty carefully to decide if you've got if it makes sense to use the gas only, or if a heat pump is worth considering. However, once we get into energy performance, so this is the looking at if we are how much energy do we energy approaches, how much energy would you use? If we want to reduce our energy use, then we want to look at the various approaches, and no surprise, the economic point has got the highest energy use, because the heat pump options are going to have a COP on an annual basis around 2.5 or so. So there's a good energy savings to be had if we use one of those approaches. And again, not a big surprise if we're using the two-stage temperature approach. What that does is it runs the heat pump for longer, so there's going to be less gas backup. And the third consideration is our greenhouse gas emissions performance. Here we're using the Alberta emissions factors of 187 grams of CO2 per kilowatt hour for gas and 540 grams per kilowatt hour for electricity. So we can see there's a fairly large discrepancy here between gas and electricity, but nevertheless, gas still has more overall emissions if it's the economic balance point where the heat pump is not used very much at all, and the other two will have less emissions, even though the emissions factor is higher. But because of the COP, we do get lower emissions on the when we're using the heat pump. So, what are the advantages of each of the four approaches? If we're looking at reducing reliance on fossil fuels, either of the two approaches where we either two-stage temperature based or two-stage time based do give us reduced use of fossil fuels. We've got reduced operating costs on the gas-only approach, or the single economic point. I keep saying gas only, but that's because there's so little electricity or so little heat pump use when we're looking at the economic standpoint. And then if we're looking at, it's not on the chart, but if we're looking at reduced emissions, then the approach 3 and approach 4 are go-tos there. So what do we see? There are various controls in the marketplace that will allow us to use different approaches. We've got at least 4 different approaches here that we've looked at, and those strategies have got real impacts. They can result in costs savings over the years, and even there's a potential for cost savings. The reduced emissions don't necessarily relate to lower operating costs, so there's a little altruism, I guess, needed there to consider some of the approaches on saving the planet, if you will. The energy cost changes are going to have a impact on what the savings are if we're using the heat pumps, and the ratio of gas to electricity costs are the major economic driver, as is the COP of the heat pump. So it's important to know what heat pump we're putting in. Then there are some other control issues that we want to be aware of. Heat pumps don't operate the same as a gas furnace. The output temperatures are lower, capacities are lower. So one of the things is we want to have minimal setback due to long recovery times with heat pumps. So we really want to operate them as with only a few degrees of setback at night or when we're away. And I didn't mention it, but all of those examples were also the same in that they had no setback. Their heat pumps can come with dedicated controls, or some heat pumps will accept third-party thermostats. And the dedicated controls can be a little more expensive, but they can also be much more functional on the heat pump itself. That is One of the things that happens with heat pumps, especially cold climate heat pumps, is that they have got variable speed compressors. Excuse me, non-communicating heat pumps or third-party heat pumps may not be compatible with variable speed. There's sometimes only a two-speed option for the compressor. Um, Although I am seeing some heat pumps that will do variable speed, but it's based on an algorithm built into the unit and uses its own outdoor air thermostat to uh, provide that variable speed control. Um, and so it's not necessarily going to give you the same performance as the dedicated thermostat that is communicating comes from the manufacturers. Um, there are some manufacturers where it is a communicating thermostat, but what it looks at is not one of the strategies that I talked about today, but rather it is it looks at how fast the space is recovering and brings on the backup when the space isn't coming up quickly enough. And I've seen that this brings on the backup heat at the strangest times for the strangest reasons and is not a very energy efficient strategy at all. Um, and these controls can also be somewhat complicated to set up. So we want to be careful that when the installers are putting them in, they do know how to, they have been factory trained basically and are able to set those up properly. Um, when we get into selecting heat pumps themselves, there's a couple of things we want to be aware of. One is using proper F280 approved software. F280 is the Canadian standard for doing a heat loss on a house. And we want to be really careful not to use a like for like. So the heat size and trying to size the heat pump for what the what the if it is a retrofit, what the existing furnace is, because existing furnaces can be up to 40% and even more oversized for houses. The example I showed, I think it was like 35% oversized, was the furnace that was in there. So that's a doing a like for like exchange is not a very good strategy. Or a rule of thumb is like the tons per square foot that some people use. Um, the next thing to do after we get a proper heat loss is make sure we know what the maximum capacity of the existing ductwork is. And the flow and static should be measured, not something like measuring the trunk size to see what it can handle from using a duct calculator. Um, and this is important because heat pumps are low temperature devices, so you need more CFM for a given capacity because it's being provided at a lower temperature rise. Heat pump performance. Heat pumps now have HRI ratings at up to 5 outdoor air temperatures. So you can develop those curves for capacity and for COP that I was showing earlier. And one really nice tool that's out there now is it's developed by Enercan. It's called the Air Source Heat Pump Sizing and Selection Tool, and it provides assistance on doing the energy analysis, understanding the load and capacity curves, determining key settings like that balance point. And it is available on the internet, and all you need to do is use Google and go to Leap Heat Pump app, and it will provide both a Excel, downloadable Excel version and an online version of the tool. The download for the Excel-based tool looks like this, and you can get the sizing tool, a selection tool, a new selection tool, and an addendum that goes through worked examples to help you be able to use the tool properly. There's also now, just within the last couple of weeks, actually, the tool has been put on the internet, and it can be used on the net. You have to set up an account with it, and you put your projects in there. And it is a little more rudimentary than the Excel-based tool, but they are updating that continuously to get it. It is fully functional, but more functionality to it, I guess I should say. So that's it for this. And yeah, if we've got questions, happy to answer.
Excellent. Yes, thank you very much, John. So I think maybe I'll put two kind of thoughts that I've got from this presentation, and then I'll go over some of the questions. So I think the biggest thing that I've learned, or it's reinforced, is that for different types of houses, if we're doing deep energy retrofits or shallow retrofits, the heat pump and the gas hybrid system is a good option. What I think we want to make sure we're starting to get rid of is that air conditioner and gas furnace, because that air conditioner costs similar to a heat pump, but can't give us any of that heating options. So if we just stop selling air conditioners, put in heat pumps, that at least would give us all these access to all these different ways to control that, to help start using more electricity and less gas. And the other big thing that again, unfortunately, I knew this, but I've learned again, is that gas is too cheap in Alberta. And since we use gas to make electricity, when we're buying electricity from the grid, it is still fairly dirty. So I think that leads me very well into what a number of the questions were circulating around was, is there a different way, or is there a calculation tool that can account for more on-site solar PV generation, which obviously has a much low greenhouse gas emissions and a much lower cost? Is there any tools that can kind of bring that into account, that if we're self producing electricity from our solar panels on an annual basis, would that change, or can that be incorporated, or has it been incorporated?
Good, very good question. And my honest answer is I don't know. I can look into it, but I think if you look into the tools there, they do use some the greenhouse gas factors. I suspect that they're using just the sort of a annual factor like I used in these. I'm going to guess that it isn't really available, but it's not a hard calculation to do yourself. I mean, if you've got an annual energy use, and if you've got, say, you're using 50% of your own electricity with zero, and 50% of the grid electricity at 540, you simply cut whatever your greenhouse gas number is from that in half, because you've provided half your electricity, or whatever the fraction is. So it's a fairly easy thing to do yourself once
Yeah.
once you've got the greenhouse gas emissions from one of these tools.
Okay, because on those tools you self enter. It's not a drop down for the grid intensity. You enter that number yourself.
No, I think it's a drop down. I think it picks it from your location, so you're from your province.
Okay, so we might have to
But
pretend that we could do that calculation ourselves, and we pretend that we're like in BC or Ontario that has a lower grid number that looks that way, and then makes
that's
us look like we're there.
that's another. Well, yeah, that I'm not sure that that would work, because then it also assumes you've got other factors that go with the electricity grid there, like the costs and whatnot. So I think it might be a hand calculation after the fact.
Okay, excellent. So I think you did touch on this. Another question. So all of those calculations, they're excluding for both electricity and gas the fixed connection fees because we're assuming we're keeping gas and we're keeping electricity, so those fixed connection fees are there regardless, right?
Well, they actually aren't even there. They're on top of those costs. Those costs are only the variable portion of the cost. So if it said 1,500 or $1,300 a year, and you had $20 a month for a fixed fee plus GST, you'd have to add those on top of those costs.
Okay, excellent. Um, I guess since I guess some of us are going further down that pathway to net zero carbon, net zero energy, even though you didn't talk about it in your slides, could you talk about some of the ways that we could possibly do an all electric, like a heat pump with electric backup, and how we could control that type of system?
Yeah, they absolutely. So that sort of system would be again very similar in that you would have your thermostat, and it depending on the manufacturer. Some manufacturers allow you to do some different strategies like that if you're using their dedicated system. If you're using a third-party thermostat, then you would uh, have the parameters set up very similar to either any of those strategies that we talked about here. And the only difference would be that instead of bringing on the gas, turning off the heat pump and bringing on the gas, it would keep the heat pump running and then put the electric heat on as well. So it's yeah, the strategies would be either one, what the manufacturer has built into their thermostat if you're using a dedicated thermostat that doesn't have these options, or if you can any programming that you can do with it for a gas backup would also work on the electric backup. Except, as I say, they would both run simultaneously rather than one or the other, as with the gas.
Okay. And I guess I might add, just because Passive House Alberta did a small survey with some index funding, that if we're trying to reduce that peak load, we ideally don't want the electric resistance backup and the heat pump compressor running at the same time. It would be an either or, because if they run at the same time, they obviously have a higher peak load impact than if just one or the other is running. So depending if you're trying to stay on that 100 amp circuit or not, you might want to change whether or not you can run simultaneously, because that would give you the best comfort versus turning off one and running the other to keep your peak load lower.
Right. And well, like that we can go further down this rabbit hole. There's so on most of these back electric backups, they are not an on-off situation. They are either a staging, so you go one stage, two stage, three stage, or they could even be modulating with so that it only adds what it needs to maintain a given supply air temperature. So you don't, if you've got a 10 kilowatt backup heater, you might only using 1 or 2 kilowatts, at low peak times, and then more as it goes on. And the second option is smart electrical panels. But you can actually get uh, the breakers that are smart breakers that will turn off certain loads so that you can use the heat pump load. So if you've got say electric water heater, you can turn off the electric water heater. If you've got an electric car charger, you can turn off the electric car charger while the heat pump is running, and then bring the other one back on, so that you can maintain a smaller panel and not need to go to. So there are a couple of options there, but it gets fairly technical after a while.
Yes, it does. Excellent. Um, so the question around, I guess, for these hybrid systems, are they maybe better suited for a retrofit project that might need the mechanical system first and hasn't done all the building envelope improvements? Because what we're seeing, or if you can do all the building envelope improvements and reduce that load, then maybe you don't need the gas backup as much. So I guess, can you talk to maybe when this hybrid system is most useful, or what could be part of a larger pathway?
Well, I'm really glad you brought that one up. Uh, with any heat pump installation, the very first thing we should be looking at is improving the energy efficiency of the envelope. So whether it's new construction or retrofit, we should be looking at what can we do first to reduce the load so we can minimize the size of heat pump we need to put in. Um, the gas backup, yes. If you've already got a gas furnace, then that's a really it's probably as good an option to put in a gas, keep the gas backup. And again, to your point of is there a if you've got a small electrical panel, 100 amps electrical panel, and you don't want to upgrade, or it's going to cost a lot to upgrade, then that's a great time to use a gas backup for it. Um, if you're going into a new house and you've got an energy efficient house to start with, you've got a small heat pump, you can and you don't need or you can put in a 200 amp panel to start with, then the electric backup can make a lot of sense in that situation.
Excellent. Um, can you talk a little bit about if we're, say, using an air to water heat pump as opposed to an air to air heat pump? And is, I guess, is the distribution method any different? Are the controls any different in that type of equipment?
That's a completely different animal because you're heating usually heating a storage tank that you use then to distribute the heat through the house. And you're not at because you're using storage, it's not a simultaneous heating situation. So your controls aren't saying, is my house too cold? Bring on the heat pump. Your controls are saying, is my house too cold? Give me heat from the storage. Is my storage too cold? Turn on the heat pump. So you've got a lot more flexibility in when you run your heat pump and your storage than you do with an air-to-air heat pump. So the control strategy is completely different, and that would be a topic for a completely different another seminar totally.
Excellent. But I guess so, so by using the air to water, you could do a little bit of time shifting, such as that you could have a bigger tank. You warm up the tank maybe when it's sunny using your own generation, and then when the sun goes down and the grid intensity, CO, greenhouse gas emission intensity goes up, then you're using that kind of stored energy at that time.
Absolutely. And then there's all kinds of you mentioned what's your distribution system. If you've got say a basement floor that has you can put the piping in the floor to use the a radiant floor, you can use that floor as storage as well. So there's some interesting things you can do with air to water heat pumps that aren't available with air to air heat pumps. And you're right, that storage and the peak shifting is a huge item in air to water.
Okay. How about, I guess, ground source heat pumps? Are they normally air to water, or are they air to air, or is the control strategy similar or different for ground source heat pumps?
Well, ground source heat pumps are basically a water to water heat pump because you're running normally you're running water in the well in the boreholes, and then you're running water into the building. So again, completely different animal depending on whether you're using storage, you're not using storage. Um, and the controls are again really quite a different animal in that you are well it yeah it's the it can be similar if you've got no storage. It can be different if you've got storage. So again, ground source is a animal unto itself, or a topic for another seminar.
Yep. Yeah, but I guess a good way to again kind of reduce your peak demand because the capacity of ground source heat pumps don't drop, so they stay very consistent. So you don't have to use, or you don't really need a backup of any type for ground
Uh,
source, correct?
yeah, that's right. That's right. Ground source is much again, it depends on whether you're using vertical borehole, horizontal bore field. There's differences there too, where it can be. You generally shouldn't need backup in it, but you might have a bit of backup depending on exactly what the system is you've got.
Excellent. All right, so that's most of the questions. Any of the people that asked the questions, do you want to unmute and either ask a follow-up question or ask it slightly different than the way I did? This is supposed to be a conversation not just between me and John, but with other people. So for those on the call, if you want to unmute or put up your hand, that would be fine.
Hello.
All right. Yep, go ahead.
Yeah, I was the one that asked about the envelope improvements and ventilation and so on. And I guess I was more going along the lines of how the economics or the analysis changes as we shift that balance point to colder temperatures where the heat pump's not really operating at a good COP so much. So if you have passive house envelope and good windows and heat recovery and ventilation, and you're also taking solar gains, then really the temperature, the balance point where you actually need to be adding heat from the heat pump is just kind of the overnight hours in those um, kind of shoulder seasons. And so, yeah, I guess it was just more just a commentary of what you think is the strengths relative, improving your envelope and windows versus the heat pump, and yeah, just that kind of thing.
Well, thanks, Mauricio. Nice to see you're here. The issue there is also when do you start heating, because you're heating your point at which the heating in the house starts is actually quite a bit lower, or can be quite a bit lower as well. Where one house might have say 17, or not an energy not non-energy efficient house might have a 17 or 18 degree outdoor temperature at which you start heating. A really energy efficient house might be only 10 or 12 degrees before you have to start heating. So even there, it does go down. Um, the You're right. The COP could be expected to go down because you're going to be running at, well, are you going to be running at colder temperatures? Uh, the uh, the balance point is really about what temperature um, does the capacity of the heat pump versus the heating load of the house come in. So your heating load of your house is a shallower slope. Therefore, if you've got the same heat pump, yes, the curve will cross at a lower temperature. So you are going to be going to a lower number. But then you're also going to be using a lot less energy overall. So I don't think it's a simple matter of, because my COP is lower, my costs are going to be higher, because you're actually going to be using a lot less energy overall. So I think that's a point where you have to do the analysis to see what the answer will be, because uh, you've got two unknowns there, not one, if that makes sense.
It does, yeah. Yeah, I wasn't looking for a definitive answer. Like I said, it was more commentary because it does throw a wrinkle in things. And I guess if you're looking at a retrofit, there's limited budgets and so on. And so, yeah, it's more about just to think carefully how you can just improve the overall efficiency. Yeah, and how to reduce greenhouse gases, maybe in other ways first. But yeah.
Absolutely, totally. That you hit the nail on the head there. You want to make sure that the house is as efficient as it can be to start with before you start putting in the before you go to the heating system. And that's something people really need to understand is the building envelope and ventilation system are as important as just as important a part of the heating system as is the heat pump or the gas furnace or what have you.
Right on. Thanks.
Yeah, I think it's always that it should be efficiency first as much as you can, and then your mechanical systems second. But I guess when we're looking at some deep energy retrofit plans, if your furnace is dead now, you kind of have to replace it now. So this, again, the different options on depending what you can do in what stage will vary the responses to your deep energy retrofit plan.
Absolutely.
All right, anyone else want to unmute? If not, we're getting near to the end, and John, you had to go right at 1. So yes, I'll give everyone another minute or two to answer any or ask any last questions. If not, I will sign off.
Frank, and I might have missed it if you'd asked this already. I just thrown out a question there about is there more than just the 4 control strategies presented here, or is there other less common ones that are available?
Yes, there are. Good question. Yes, there are other strategies that are available. The one that I mentioned was the rate at which the house starts to, or a rate at which the house warms up when the heat pump comes on, and that's a sort of a dedicated strategy in a particular heat pump or a heat pump controller. They're not even called thermostats anymore. They're called controllers now. And there probably are some others that are out there, but these are probably the most common ones right now.
Thank you.
All right. Well, we're coming up to the end. So this is the last Buildings Better in Alberta webinar for the year. We'll be back in January. So thank you to Alberta EcoTrust and to John Kokko, and have a good day.
Thank you for inviting me. Bye, everybody, and thanks for joining.
Thank you.
Okay.